Right. So I just wanted to first do an introduction of who's going to be presenting today, just so that you get an idea of who we are and how we fit into the C6 forum. Slightly in reverse order of speakers, but you're going to have, so KangKan Shen is Chief Architect for System Firmware in Huawei. He's a chair for the C6 Firmware Group. He's also firmware lead in the C6 Software Group. Within the Linaro Data Center Group, which is the part of Linaro that deals with server-based systems, he leads. He's a steering committee member, and so we're going to talk a little bit about Linaro projects to do with C6 as well, and KangKan will speak to that. And also within, he's very, very active within the UEFI forum, but he asked me to mention here the heterogeneous memory subsystem, subteam, sorry, which he leads. Which deals with some of the UEFI and ACPI stuff that we'll talk about later. Thanu Rangarajan is with ARM. He works as an OS software and firmware technical lead. He's in the C6 software and firmware groups. He's a lead for the firmware, and actually we've got to thank him because he's prepared pretty much most of the materials here today. He's a key representative for ARM in UEFI and ACPI as well, so essentially really a firmware expert. And finally, there's me. I'm an OS architect and fellow here at ARM. I am sort of responsible for a number of standardization initiatives, particularly around software and operating systems and firmware interfaces, and that includes C6, of course, but also UEFI, CPI, and other servery stuff. So with that, let's start. I'm going to describe, can we move to the next slide now? I'll describe what we're going to talk about today. So there's sort of 4 parts that we're going to talk about. The first part is going to be me. I'm just going to give a very high level overview of what a C6 system looks like. Some of this material will be familiar to people who've been to the other webinars, but it's without it, it's just kind of hard to put the whole progress that we've done on software and firmware into context. Then in more detail, Thanu is going to run through part 2 and some of part 3, describing the actual interfaces that C6 provides to do things like management and software discovery. And then finally, KangKan is going to talk a bit in more detail about what an implementation would look like and how that affects actual UEFI and ACPI, and also provide a kind of a high-level overview also of what the virtualization story looks like, and a bit of power management, and finally end with a little bit of status update. Cool. So let's get into part 1. So what's the overall, what does a C6 system sort of look like to software? So the first thing to realize about the C6 system, of course, is that it's composed of a number of different C6 components. You can think of a host system, an SoC with a set of processors that are facing to the operating system that connects to a C6 device, and the C6 device inside it contains things like accelerators and memories. We're going to go into all the detailed components, but essentially we'll talk about request agents and home agents and slave agents, which are the RAHs, NSA mentioned down there, and the accelerator function calls, which is the AFCs. Well, we'll go into a bit more detail of all these later, but it is just to give you a high-level overview. The other thing that C6 components connect to each other over C6 links, and the C6 links egress or ingress, or merge out of and come into C6 ports. Should we go on to the next slide? So, yeah, thank you. And because of the fact that you can think of a C6 device as something that contains accelerations or memory functions that are connected to a host system, you can actually produce quite a number of different topologies for C6. And so in this slide, we've just got a few example topologies. So for, I guess the first two topologies are a bit tree-like, and then after that there's two examples of mesh topology. So this is where it differs from something like PCIe, which is always tree-oriented. C6 devices connect to each other over point-to-point links, or C6 links. Next slide, please. And in terms of use cases, there are primarily two types of use case within C6 that we're trying to deal with. So the first one is accelerator engines. So we have an accelerator that's coherently attached to a processor, so it's able to participate in the host processor systems cache coherency. An accelerator therefore can use memory that's in the host system, but it might also have its own memory attached. So C6 also comprehends the idea of a C6 device containing memory. And that gives rise to the second major use case category, which is simply coherently attached memory, whether it's volatile or non-volatile. C6 devices might be essentially just providing expansion memory, and which would be cacheable and coherently presented to the system. Next slide, please. So if we look at the accelerator use case, if you look at it as an C6 accelerator, it's sort of broadly composed of two parts. On the one hand, we have what we call accelerator function calls. These are essentially or the accelerator compute engine, the bit that actually provides the algorithmic support to accelerate something. The actual an analogy to this in a regular computer would be a processor, if you like. And the accelerator function calls, one of the things that marks C6 as being different from other standards is that the accelerators run coherently with the rest of the, participate in system coherency with the rest of the processors in the host system, and therefore can read in and out of caches and have their own caches as well. Mean processor caches, but also have their own caches as well. And to the software, all of this is transparent. And the way this is done is through a C6 component called a request agent. So behind every C6 accelerator function call, there might be one or more request agent, and you can broadly think of the request agent as the bit that's providing the caching and the participation in coherency to the accelerator function. So that's roughly what a C6 accelerator looks like. Next slide, please. Thank you. So the other use case that we talked about is memory. The way C6 organizes its memory is that it has a concept of a home agent. A home agent is basically the agent that receives memory access requests for a particular region or set of regions of physical address space. We will talk later about what we call the system address map or global system address map, which is essentially the global physical view of the address map seen by all of the C6 participating agents, including CPU processors, traditional host processors. And you can think of chunks of this global address map as being owned by a particular home agents. The home agents then might actually have their own memory pools built in, they might actually have their own DRAM or some form of non-volatile memory attached to them as part of the home agent, or they might actually allow the memory to be plugged into them through a second C6 device called, or third C6 device rather, called a C6 slave agent. We've got an illustration of this on the next slide. That was a cue, Thanu. Hey, sorry, there's a bit of a delay on these slides. So CCIX, as mentioned, so you might have so in the figure here we're illustrating a C6 device that has a home agent that has its own memory. We call the memories memory pools, and Thanu will expand on that later because memory pools literally translate to specific regions of memory that are behind a particular agent. And so here in this example, memory pools 1 to n are directly behind the home agent in one C6 device, but there is an additional memory pool n+1, which is on an extension device connected through C6, and this device is served by what we call a slave agent, and that's how we can do extensions. You can have C6 devices that just contain slave agents, and they literally just contain memory and require another C6 device to do the homing. Cool. Next slide, please. The other type of component, if you like, that you have on C6 that we sort of briefly alluded to earlier is C6 ports and C6 links. So C6 devices connect to each other over links, and the links come in and out of ports, and essentially these structures then relate to individual bits of configuration that boot firmware has to do to enable the communication to take place and to bring up the links. And we'll talk about this later in a lot more detail. A device might have also typically a device can have more than one port. It's worth mentioning because the device will always have a primary port, and a lot of the device-wide data structures, which we'll describe later, are described alongside that primary port. But it can also have secondary ports for connections to other C6 devices. And now that we have this mental map of, okay, so I've got devices, they have home agents, they have request agents, they might have slave agents, they connect to each other over C6 links, which go in and out of C6 ports. We can talk about the kinds of messages that flow across those links and between those types of components. And the messages are either essentially memory requests, so which is why request agents are called request agents, because they're requesting memory accesses, read and write memory accesses. Or there might be snoop requests. So a memory request is going to flow from a request agent to a home agent that's homing that particular address range that the request agent requested. A snoop request is going to go the other way around, from a home agent to a request agent, because the request agents are the things that have the caches in them. And so when a home agent sees a request for a particular memory region, a particular memory address, it's going to check to see which accelerator might have that, which request agent might have that, and send it a snoop request to try and pull that data. So those are broadly the two types of messages. We'll also see later that we also do have RAS messages to do with error management. RAS relating to error management. And those are the basic message types. Thank you. One of the things that kind of, as you build this picture, one of the things that obviously emerges is that because C6 devices might connect to each other over more than one link, because we support not just tree-like structures but also mesh-like structures, we have to program the routing as part of the bring up of a C6 based system, because the path between a request agent and a home agent, or other way around, will have an ideal routing, and improper routing would lead to drops in performance, or even increase in power management and power consumption. So routing is one of the big jobs that we'll talk about as part of one of the big software challenges that we have to do, which we're going to do in boot firmware, and we'll describe in detail later. That's one of the big challenges we have to address. To help with this, and to help with the routing, and to provide the backbone as to how the C6 actually works, every agent has a unique ID. And the types of messaging that we provide in C6 might be ID rooted, or as we shall see later, can also be address rooted. ID rooted message, an example of the canonical example of an ID rooted message is a home agent asking for a snoop request. So as part when the home agent learns that a request agent is looking for a particular area or trying to access a particular area of memory, it'll then send snoop requests out, and those snoop requests are sent via ID routing. Another example of ID routing messages is reliability and availability, serviceability, RAS messages, which we'll briefly touch on later as well. Then the other kind of messaging that we talked about earlier is address-based routing. In order to be able to do address-based routing, every home agent needs to own a set of memory regions, as I mentioned earlier. Oh, we've jumped a slide. And so we talk about there being a global system address map, which really is a software concept rather than actually having a physical manifestation in terms of registers. But when firmware is trying to bring up the system, the first thing it does is it creates this global system address map, which basically specifies which region of memory is owned by which home agent. And then it uses that when it's trying to program the individual routing from one C6 device to another, because essentially what this global system address map is really saying which particular C6 devices own which regions of memory, and how you communicate between, and how to route between the different devices. So again, it's really important for boot time firmware to get this routing right, because that will give the optimum performance. So you can therefore think of a C6 system as a network of C6 devices. You can even consider the host system itself as being kind of like a C6 device. Processors in the host system are effectively request agents from a C6 point of view. And any memory homed in the host system is essentially the host system acting as a home agent from the point of view of the other C6 devices. So that's essentially roughly what a C6 system looks like, and that's what a C6 system will look like to software. And the important thing is that firmware needs to then program the routing so that all of the messages can work in the optimal way. Next slide, please. So if you then think about it just from a memory access point of view, because there is routing involved, and because there's potentially more than one, and because there's more than one domain that might contain memory or processing, you can think of a C6 system as being composed of a set of initiators and a set of targets. By initiators, I mean processes that are requesting memory accesses, or accelerator function calls that through a request agent are also requesting memory accesses. And the targets are the memories. Now, if you have a network of devices with different devices owning different either initiators, so request agents and processors, and other devices owning memories, and then the path between any two, any initiator and any target, is going to have a different performance characteristics associated with it. So really, it is actually a NUMA system with every pair of different initiator and target having a different bandwidth and latency associated with it. I think this is illustrated on the next slide. I guess I kind of spoken to this already, but so you can imagine that, for example, for processor 1 to access memory 1 is going to be a lot quicker in this example than for processor 1 to access memory N in the expansion memory C6 component on the bottom right. So much how we've already dealt with NUMA systems at a processor and SoC level in traditional say dual socket or systems, for example, or N socket systems, C6 extends this, if you like, to create more NUMA domains associated with the individual C6 components. Next slide. And so to deal with this NUMA problem, we've actually generalized the concept of, we've generalized the data structures that ACPI uses for NUMA, and KangKan is going to talk about that later, and this is something that's going to come in the next revision of ACPI. Another aspect that we haven't touched upon that much, but we've sort of mentioned briefly, is, we've mentioned that accelerators can have their own memory, which can also be a part of the C6 system. So for example, I could have a C6 device that has a set of accelerator calls, an RA to provide caching for them, and then a local home agent with its own memory, for example. And obviously that memory being local to the accelerators, you really want to use it primarily for that purpose. So we've also provided ways to describe to the operating systems which memories are more for a specific purpose, as opposed to for generic kernel and application use. And we'll talk about that later as well. Cool, and at this point, I'm going to hand over to Thanu, who's going to go into a lot more detail. I hope that was useful as a kind of high-level overview of the C6 system. And Thanu's going to go over in a lot more detail as to what the hardware and software interfaces look like. Thanks.
Thanks, Charles. I hope my voice is audible, and I'll go on. Okay, so obviously we have a pretty good sort of overview of how a C6 system would look like to software. But then for software to be able to configure that system and make it up and running for runtime use, it relies, or it would need to rely on a set of interfaces that the hardware needs to provide. And so in this section we talk about those interfaces and see how they help eventually, as when we go on to the boot firmware description and the runtime OS frameworks. We'll see how these interfaces would be useful in accomplishing those tasks. So at a high level, so the 1.0 version of C6 is sort of inherently reliant on an underlying PCI transport. So which means that, as if you recall, Charles did mention, he did briefly describe the concept of a C6 port, and he did talk about C6 links. So effectively, a C6 port is effectively a PCI port. It's sitting on top of a PCI port, and therefore it leverages an underlying PCI transport. So having said that, so that's really a first level of dependency. And if we have that first level of dependency, I must mention that once we have the PCI transport underneath, then it's possible to transmit or communicate C6 messages over that transport. So that becomes a sort of a conduit. So that's the first level of dependency on PCI, and we sort of expand on that. And I move on to the next slide and wait for it to build. So having said that, so we have the various components that Charles talked about, and obviously the the hardware needs to provide a set of CSRs, configuration status registers, in order for software to be able to program these components. And programming these components, for example, like Charles talked about agent ID. So we want to be able to program an agent ID into, let's say, an array on a C6 device. And in order to accomplish that, we need a set of CSR, registers in order to do that. And therefore, these registers would need to be architecturally defined within the C6 device. I'll move on to the next slide, where because there is an inherent dependence on an underlying PCI transport, we use the standard PCI paradigm by locating the C6 CSRs in PCI configuration space. And more specifically, the The C6 registers or the C6 register structures are located in PCI extended capability space as a DV6 structure. And the DV6 structure is specific to C6, and it will have a specific PCI-SIG assigned vendor ID that would then be able to be put to use for software to be able to discover C6 devices in a given system. And the rest would follow as part of the standard PCI discovery flow, as part of the standard PCI bus walk. And as you can see on the right, you have the protocol layer DVSec, which houses pretty much all the CSRs pertaining to the various components on a standard C6 device. And there's a subsequent slide that will detail how these CSRs are laid out. Within the protocol layer DVSec region, the C6 CSRs are sort of split into two logical regions. The first region pertains to the capabilities and status registers, which primarily provide a sort of a read-only capability. And the second set provides a set of control registers through which software can program things like agent ID, routing tables, etc. And we'll touch upon those as we go along. But at a high level, this allows us to have a fairly clean split between capabilities and control, and so they pertain to each component in a standard C6 device, so that it creates a nice sort of clean partition between these capabilities and control registers. So a little more elaboration on this. So the Charles did briefly talk about primary ports. So the primary port is the port, as as we learned earlier in the webinar, that a C6 device could have multiple ports. So there's one port that's sort of elected as the primary port, and that has all the device-wide component structures, being registers, and that port is called the primary port, and the function 0 on that primary port would have a set of device-wide component structures, and that's illustrated here. The other non-zero functions can hold agent-specific component structures, so they need not have device-wide component structures, but they can still have regular agent-specific component structures, and that allows us to have a fairly clean way to not only discover capabilities specific to the device as a whole, but also to individual components. And it also allows system designers to effectively place agents in physical functions, and thereby sort of extending the reliance on PCI. And it enables also a standard programming model that PCI offers. Okay, so I'll briefly touch on some of the global device-wide structures because they are sort of fundamental to the whole discovery process and the boot firmware flow that we will be talking about shortly. The key structures would be primarily what we call as the ID map table or the IDM table, and the system address map table, which is the SAM table, the acceleration function property table, which and then there's the device ID, and I'll talk about the device ID in some detail shortly. Moving on, we'll very quickly describe what an ID map table is. So as Charles described earlier, right? So you in a network of in a C6 network where there are a set of like C6 devices that are interconnected to each other, and each with a set of agents on it. In order for agents on a given device to be able to communicate with agents on a remote device, the local agents on that device would need to know how best to reach the remote device and agents thereof. And the ID map helps those local agents to recognize which egress port they need to be sending the C6 message to. So it's really a form of an egress port and an agent ID, and there's an illustrative example here where you have simple um, ID maps to show where remote agents are located. So, for example, if HA3 needs to send a snoop request to, say, RA0, it would primarily send it on port 6. So that's the kind of like intuitive intelligence that one would need to build into the device, and the ID map provides that intelligence for agents on that device. So again, Charles did mention ID routed messaging, and so this is really about all about routing ID routed messages. So moving on, the like the ID routed messages, there's also the address routed messages, which are primarily targeting memory pools on remote devices. So let's say if you have an array on the local device and it needs to understand, where in the global system address map, uh, the memory pool residing on a remote device is, then it would sort of consult the local SAM table to understand which port will lead it to its memory request to the right memory pool on that remote device. So the SAM table, just like the IDM table has an egress port and address range tuple, and it enables address routed messaging, which is the second type of messaging that we just learned earlier in the webinar. Right, so moving on. Right, so the third type of important global device-wide data structure is the AFC discovery table, or what we call as the AF properties table. The AF properties table points to where the location of AFCs on a given accelerator, C6 accelerator device, which has basically AFCs, and it also has the associativity between those AFCs and their parent, array. So, like we learned earlier, arrays basically function as the front-end cachers for memory requests coming in from the AFCs, where AFCs are housing sort of compute engines where you do the acceleration, and therefore there needs to be an association between an array, which is sort of the caching agent, and the AFC that relies on that array for performing that caching. And so the associativity information is sort of embedded in the properties point properties table as well. A bit more on that, a little more elaboration on the same concept. So the idea is that once you organize AFCs into clusters, we are calling them as clusters, to sort of understand how what's the sort of internal logical hierarchical arrangement. But the idea is that once you have the AFCs associated with a parent array, then it aids in a couple of things. One is the ability to associate AFCs with arrays, and for certain use cases that I won't be delving into today, but where you would have the need to understand which arrays acting as the front end cache for a bunch of AFs. But a more intuitive use case is power management, and that's because if you want to have, let's say, a device should be able to, a C6 device should be able to support power management, and in order to be able to support that, it needs to have a very clear hierarchical sequencing where, once the AFCs are quiesced, then it's only natural that one would want to quiesce the RA that's acting as the front-end cache for those AFCs, because arguably that RA is at that point idling, right? So that's where the associativity is useful. Okay. A quick note on the CCIX device ID, which is the last of the key structures that we'll be talking about today. So if you look at the, so Charles had mentioned the a C6 network where you have each C6 device potentially having more than one port to which it could interconnect with other C6 devices. And now we also talked very briefly about the reliance on PCI to establish that topology, if you will. Now, in a mixed topology where you have a standard system with legacy or native PCI endpoints and C6 endpoints, you can still go ahead and discover C6 devices, and we'll touch upon that when we talk about the boot flow. But very quickly here, what happens is that when you have a C6 device that is essentially a PCI device, if you look at a legacy PCI buswalk routine, right? You need to be able to, when you could reach that PCI, that C6 device through any of its ports, depending on how the topology is laid out, and in which direction the buswalk begins, or from which direction you reach that C6 device during the buswalk process. Now, where the device ID helps is that if you once you visit a C6 device, you need to be able to remember that you visited it already once, and just in case you do happen to visit it again through any of its other ports. But it also helps in establishing the sort of logical relationship between the ports, and thereby identifying these ports as being the sort of the boundary of a C6 device, and thereby knowing that there's actually a C6 physical device that these ports are a part of. And this helps with the overall topology discovery process, as we shall see in the following slides. Right, and this is an elaboration of how the device ID is programmed. So the device ID is actually part of the again the device-wide common control structures, which are in the primary port. So it ideally should be able to reach the primary port on the device and program its device ID, and then that device ID essentially the process that the device, as per the C6 architecture, that the device follows is that once you write the device ID on a given port, it's replicated on all the other ports, and the other ports automatically become secondary ports, and thereby sort of linking the ports together into a logical sort of cluster, if you will. How this would help in the overall boot flow and the topology discovery process, we shall see shortly. Final component structure that we thought would be useful for us to talk about today would be the per logs and the per messages. So the per messages are unique ID rooted messages that target a specific C6 agent called as the error agent. Typically, the error agent would be obviously in the host system, where it would be acting as a sink for all the per messages that would flow in from the C6 network from devices that are reporting errors, obviously. But the error agent could be anywhere, actually. So, but it has a unique ID that needs to be programmed by boot firmware, and it needs to be also it needs to be able to. So once you program it as the error agent, then it essentially functions as a sink for messages, and you need to the firmware needs to program the routing tables accordingly. so that per messages would flow to the error agent eventually if they do occur. The other important thing is that to assist with the error agent to do triaging, it's important that the C6 device maintain some kind of an error syndrome information. This is very reminiscent of the standard PCI AER mechanism, where you have a per log which is mentioned, which is sort of stored in DVSEC space, in the component structure space pertaining to the specific component. So, for example, if an RA experienced an error, then it would be in the RA specific component structure. There's a typo in there for the structure. Okay. Yeah, so like Charles mentioned earlier, the per messages are ID rooted, and precisely because they are targeted at the error agent, which has a unique agent ID. So that's sort of the high level sort of hardware interfaces, important hardware interfaces, I should say, because there's a lot more than what we had the time to present today. But these are sort of the essential ingredients that would help with important functions like boot discovery, configuration, and sort of presenting the whole C6 system for an operating system to use the accelerators on the C6 system and the expansion memory on C6 systems, on C6 devices rather. On that note, we'll move on to the software architecture, which which sort of builds on the first two parts, and it sort of lays the foundation for how a general purpose software could be written to support a C6 enabled system. So again, sort of this is like a reminder to sort of a refresher, I would say, on the capabilities that the software architecture sort of relies on. The first of which is that C6 system should be self-describing, and it is so through the DVSEC DVSEC capability in PCI extended capability region, relying on PCI obviously, and then offering a set of like configuration registers, component structures, register structures that will allow configuration and control. And then that configuration, of course, we need a boot firmware that should ideally discover C6 devices in a given system, discover agents within that system, and then configure everything so that it's up and running, and it can be used by runtime software operating system. And then one thing to note here is that the C6 host, which I think we did show in the some of the diagrams which reflect the topology, traditional topology. The host is sort of a pseudo C6 device by itself, and so it has a C6 root complex. But the design of the root complex is sort of vendor specific, and it's very again very reminiscent of PCI. How PCI sort of defines its own root complex and some of the more of the CPU complex interfaces thereof. And then, of course, we talked about the DVSEC already. And so we did mention NUMA, and we did talk about accelerators, and we did talk about expansion memory. And for a typical OS, these would be the three primary use cases that would that OS would use to manage and use a C6 enabled system. And KangKan will talk more about the OS management part. But we start with the obviously a boot process, because the C6 firmware needs to be able to bring up a system that has C6 devices in it. This is sort of roughly the responsibilities that the firmware, a standard generic firmware, C6 firmware would need to own. It needs to be able to discover C6 devices in a given system. It needs to be able to discover how they are arranged topologically. It needs to be able to then discover components within the devices. For example, a device might have an array, another device might have a mix of arrays and HAs. And there could be devices with only HAs and memory pools, which would be expansion memory devices, so on and so forth. So it needs to be able to identify the components, including memory pools. And then obviously in order to be able to establish a uniqueness for each of the agents that is discovered, that agent must be assigned a unique agent ID, and it's the responsibility of the boot firmware to do that. And that's the responsibility of the boot firmware. And then finally, it needs to stitch together a global system address map where all the memory pools that been discovered on individual C6 devices are combined with the host memory and then stitched together into a global system address map, which is not random, but it has certain principles, and we'll talk about those principles. But effectively, it helps to achieve an optimized memory addressing and memory decoding setup for the system as a whole, from host to C6 and C6 to host and C6 to C6 all the way through. Finally, then once it's done with all this, then it needs to enable the C6 devices and the components thereof, enable coherency such that the global coherency domain becomes alive, becomes active, and then it needs to then build firmware tables to let the operating system know how the C6 devices are arranged and what resources they have on offer. So a lot of text, but eventually boiling down to the flow here. It starts with host discovery. That's all the host specific initialization, which includes essentially the C6 root complex specific initialization as well. And then there's, as we already mentioned, there is an inherent reliance on PCI enumeration to discover C6 devices in a C6 enabled system, and the PCI enumeration essentially helps to discover the C6 PRL DVSEC region and the component structures thereof. Once a device that's advertised itself as a C6 device through this mechanism is discovered, then it becomes a part of the C6 subsystem, and then that device, along with the other devices that are discovered, arranged, and then the topology of that, the topological fashion in which they are arranged is it needs to be recognized again by the boot firmware. Then the components within each of these devices need to be discovered. The memory pools on the devices need to be discovered, and then the topology itself is discovered as a result of the arrangement of the memory pools and components into the device boundaries, and that's where the device ID that I talked about earlier helps. Once that is done, then effectively the firmware knows how the C6 devices are interconnected to each other in a sort of a graph, really. And then based on certain rules of thumb, which we'll talk about in the next slide, the firmware decides to then arrange to program the ID map table and the SAM tables so that the routing of C6 messages between these devices is optimum, in the sense that it results in the best performance and it results in the least power consumed in performing those transactions. And once the C6 devices are sort of initialized this way, and once the routing between them, the routing tables are sort of initialized, and the routings between those C6 devices is established, then the next task is to be able to break this topology down into a set of NUMA domains and then describe these NUMA domains to the operating system. That's pretty much the sort of high level flow. A little more detail, I guess.
It's Thanu, just to give you a time check. We need to be switching over to KangKan.
Oh, okay. So yeah, I guess this is sort of the thanks, Charles. So this is sort of the a deep dive into exactly what I just described. So it probably so hopefully it's sort of clear to everyone by now actually as to what it's really trying to say. And then we did talk about the boot firmware view of a C6 system, where a set of C6 devices are overlaid on a legal PCI tree, right? And so you can see that while this PCI, the legacy PCI endpoints are sort of hierarchical in nature, tree-like in nature, you can see that the C6 devices are arranged more like nodes in a graph. And because of that fact, the topology needs to be discovered or sort of extracted from the legal PCI tree that the firmware would discover as part of the PCI bus walk. And that's where the topology discovery piece is important, because then this leads to things like NUMA description, etc. This is sort of a walkthrough of that process of topology discovery. So it's really about pattern recognition. A firmware could employ any pattern recognition algorithm to be able to discover a given topology. But essentially, it leads up to the on the rightmost corner, right, where you see this, for example, this tree, PCI tree, is essentially a fully conducted C6 topology. A quick note on so I did mention the rules of thumb for routing. So if you take a standard C6 enabled system, if you take the middle diagram here, which shows there are 4 nodes A, B, C, and D here as an illustrative example, each carrying a set of a memory pool, the size of which is described by those blocks here, A, B, C, and D. Now the firmware could arrange these memory pools in, assign them to any SAM window in the global system address map. But it would need to do the assignment in a sensible fashion. We do have some recommendations in the software guide, which KangKan will talk about later on in this presentation. But the idea is that the arrangement of these memory pools in SAM windows would be done in a fashion that will allow individual C6 components to be able to make C6 address routed messages undergo the least number of hops as they traverse from the source component to the destination component, and same holds true for the actually the same thing holds true even for the agent to agent communication, the IDM table. So that sort of establishes a sort of an implicit, sort of inherent interdependency, mutual dependencies between routing and memory decoding. But it's sort of intuitive, I guess, in any sensible system design that you would want to achieve that. So I'll stop there. And so far I've talked only about sort of generic boot firmware principles and C6 hardware software interfaces which would assist in this boot process. KangKan will now talk about more specifically about firmware technologies like UEFI and ACPI, and how that systems that are based on these technologies today, how they can then be further enabled to fully support C6. So thanks very much, and KangKan, please take over now. Thanks very much.
Hi, I will take over here. As we have already heard before, that C6 is a very generic standard, right? It can be used in many places. Now we are specifically, C6 is on top of the PCI, but in theory, it can be on other bus also. And it can be used in a chip. It can be used in an embedded system or in a standard server. So I will like to here is make it more specific, take C6 and you apply it into a standard popular server and see how it works, how we implement it. As we know that today, most of the servers has a UEFI ACPI interface and with UEFI firmware. So we will start here. This picture shows you what is the component that UEFI BIOS has inside a server. It's lots of code, like 1 million lines of source code. And there's many components. And we want to make sure that the introducing of C6 does not change the architect of the UEFI. It's just a new add-on. So we will modify various parts, the library, the protocol, and make sure that it fits in the UEFI framework very well. And here I should mention is in C6, we have defined what the endpoint is, right? And they have DVSEG. But for C6 host, there is not a strict requirement to comply with this standard interface. So the host initialization is kind of vendor specific, need to be handled. And then we go through all the things that we mentioned, we enumeration, chip detect, right, by the DVSEG, CCIX ID, and then configuration and connect the topology. And that's one thing also is once you connect the link, if it's a C6 ESM type of link, then we need a software involvement to train the link to make sure it works on a higher speed. Otherwise, we will skip that part. And then we will set up the rounding tables and rounding table and then the memory map. So if we put them together, it looks like this is a very complicated firmware part. If you remember in the old age when we first introduced the PCI, just IRQ rounding and makes like 50% platform vendors make mistakes, and the native bridge support is a few years after PCI. So we will think there's some challenges to implement C6. So that's why we want to go a little bit more detail. Next page, please. And in C6, that this is very new, is the endpoint device ID, right? The HAID, IID, SAID, and then we have port ID and link ID. All these things to be linked together and through a few tables that we have already mentioned. I just generally talking about here is the SAM table, ID map, and the base address table, right? And these things all need to be populated, and it's a very complicated process, and because since the hardware is made such flexibility that how the C6 architect looks like, it's very much depend on how you configure these tables, right? For example, there's RA to HA, there could have multiple links, but you can you use these tables to only enable one link. And here is more details, step by step, how we found all those components and configure them. And at the last two steps, what I want to emphasize is we need to present this system to the OS. through the UEFI and the ACPI interface. Okay, next page. Yeah. So as we already know that for our standard PCO server, and the OS gets the memory map through the UEFI boot service, right? And inside the boot service, we present a memory map based on what the physical memory is inside the system. And so when we do that, we through this service, and we can have either there's basically two types of. One is the system memory. It is visible by the OS, and others are reserved memory, which is not visible to the OS. Like the GSAM is actually every memory that in the system. Some of them can be reserved for device. Some of them can be reserved by us. So this is a whole memory. And then if we can look at the specific CCIX memory, either the extended memory from SA or the memory from Accelerate through the embedded HAI at the endpoint, this memory can be mapped somewhere. And in the specs, we pretty much suggest is a 4 gig alignment, so it should be on top of the memory. So when you look at from the Accelerate point of view, that's the diagram on the right, is the RSAM, GRSAM table that for Accelerate, you really don't see all the memories, but it depends on how you configure it. You can maybe see parts of the system memory. So here is very important that in the UEFI, we introduce a new memory type called special purpose memory. So when it configured as a standard system memory, it can be distinguished from other memories. Okay, next page. And once we configured the memory, and we needed to tell the OS what is the topology, the relationship between the Accelerate CPU and the memory all together, and present a more generic numeric system. As we know that before, UEFI use SRAD, SLEET, or HMAT, this kind of a table to tell OS numer, which usually only includes CPU and the memory. And throughout the work in the past year, we introduced the concept of generic initiate, that process element can be a CPU, a GPU, Accelerate, or AI, or vector calculate, or TPU, or anything, right? And then the target can be a memory, not only the memory through the standard DDR memory controller, but also memory extended through CCIX, or linked with using other methods. The key point is we want to identify what is the distance between initiate and target, and how that target is accessed, right? Before, because it's simple, it's all cache coherence, and we just needed to know the relative distance. But now it's very complicated, is how you read it, right? How many bit cache size, or so how you read it, and it will affect how fast is the speed, is how the bandwidth and the latency of those memories. So all those informations are collected and will be presented in the future UEFI and ACPI standard, and we already get some of them in. It should be released within a few months. Okay, next page. And in a server system, as we know, we really need to take care of is our power management and the RAS, all those advanced features. And these are still under planning. But the general idea is the power management is not very different, right? We still use this ACPI supported OSPM framework. So the device will have different device state. But the key thing here is since a device, a C6 endpoint is actually associated with memory in the cache. So we introduced the concept of hierarchical or quiescence sequence, right? And before you can turn off a device or put it into a sleep state, you need to make sure and you take care of IA, HA, make sure, for example, HA don't snoop on IA, which is already in sleep, right? So this is what we need to take care of for the power management. And next thing about RAS. Next page, please. Okay, so here we are talking about the RAS standard. And RAS, we actually have a chapter in the base specs cover the RAS. The key issue is that we introduced the CCIX PER to take care of the protocol errors reporting, right? But one thing is, since C6 is a very generic standard, right? So the error reporting in architect is much more flexible through a concept called EA, error agent. But the error agent itself will be very much implementation dependent. It may depend on the different architect, CPU architect. So it's best to implement the C6 RAS in ACPI-based RAS framework. So we use the APEI, which is introduced by Microsoft in the Windows hardware error architect, right? And once, so it's a generic infrastructure, and all we need is to populate a few tables, such as error record serialization table, that ERST, and then the boot error record table, BERT, and the hardware error source table, these type of things. And if necessary, we can also do the error injection through ACPI. Okay, next page. Once we did all the firmware initialization and provide all the information to the OS, and then we move to the OS level, and we will expect that we have hypervisors, we have guest OS, and we have application, and the generic layout is like indicated in this page. And the related thing that we need to present is the C6 accelerate interface through different level, and the memory, the special purpose memory through different levels. Okay, next page. So we really don't have anything very special about virtualization, except that what we have mentioned that point to the AFC in the DVSAG, so that how the I can control different AFC. So in C6, we pretty much support all possible of virtualization technologies, like the PCIe, SIO, SRIOV, right? Or Intel's scalable IO, or ARM's Revere, whole Linux VFIO, doesn't matter it's hardware technology or software technology. It should compatible with this, and we can have configure the C6 in various different ways. Like we can put different AFC as one function and into one device, or we can put different AFCs into a functional group, like the function group, so it's controlled by the function 0. So anyway, that it's very flexible. So what we indicate here is SIOV, basically a implementation that the AFC can be directly controlled by the hypervisor. And there's one thing special about the accelerated function. If FPGA, there's inside one AFC, there's many AFTs, and those things can be assigned to different virtual machines. So that's it. Let's move on. And now we look at how OS handles this, what we have report, right? So when we have a C6, that memory is cache coherent, but the OS only knows if it's cache coherent by how you report it. And since we have to dealing with legacy OS and C6 aware OS, that we have to consider if we have a system in people install legacy OS, what will happen? So for example, when you have extended memory and you can put in the memory as reserve, so it actually not visible by the OS. And then this memory has to be managed by the device driver. Or you can put the memory as cache coherence memory as a system memory, but the OS don't know this memory is located on a remote C6 bus connected device. It could cause problems. So once we introduce the SPM and the OS can understand this is a SPM memory, then it can use it wisely, and that the memory will be managed by the OS driver. And same thing happens if the memory is put on accelerate endpoint. And as you know, that we can also configure the memory as local for the accelerate and use the user driver to manage it. And this is the current case. That is not very convenient, right? Because every different device, you have to use different drivers. But for C6, you can use the same driver. And if you report it as a cache coherence memory, that it can be handled by the OS driver. It can be visible based on how you configure the SAM. But again, that this kind of confusing is because you don't have the localization information, latency, how it connected. So only after a 6 aware the OS, we know the topology and we know where the initiator, where is the target, and we can set up a very good SVM, shared virtual machine. And so accelerate or CPU can freely use this memory in between of them. So next. And now we have shown here is a system. Now we have a cache coherence memory from the accelerate and the CPU, right? So now we can set up accelerate just like a numer before for the CPU, and use set up SDM and it can be used by the application easily without specific knowledge of the accelerate. And since C6 is a standard, it's a generic, since it's not vendor specific, so we can have develop OS drivers for power management, OS drivers for RAS, and make the deployment much easier. And the most important thing that we see here is before, when you have a system, you want to use the acceleration and hardware to accelerate certain functions. That function has to be, a certain size, because when you call the accelerate function, it takes some time. If you have a DMA, you need to set up the DMA. It could take, up to milliseconds, right? So with C6, that the setup interface will be very quick. So we can use accelerate when you have a small function needed to be accelerated, or in the case that you need to switch different accelerators, very frequently. That is very helpful. So next page. We pretty much talk about how we implement and how we use the C6 features, and what's the reality is most of those things are still under specification. We are still working on it. It's not public available, and there's probably many changes coming. So just introduce is in the software working group, we have a UEFI sub-team. We formed this team because that UEFI has some requirement that we only can allow the UEFI promoters to work in this group and make proposals to UEFI, and then once the UEFI standard published, that the whole industry can use that UEFI standard. And we have already done the SPM generic initiate. We did some this memory architect, and then there's more to work on, and we haven't done the PER, the RAS or the power management UEFI standard yet, if there's any. And we also think it's not a trivial thing. It's better that we have some kind of software reference. So we worked with Linaro, which is an open source community company, to set up a C6 reference project and implement it on a common QEMU platform, right? So all the companies can contribute on the software, and it can be used by in the future by the whatever company who want to implement C6. And we are working on also is some documentation. And before we have a firmware guide, which is done, and now we think we need to cover a little bit more. So now it got the software guide, and we are already done many chapters. And what you hear is pretty much covered in the software guide here, and that is done primarily driven by ARM and Thanu, right? And it should be ready next year. Okay, that concludes my call. I hand over to the moderator.
Hi, Matt. I think that's back to you.
Excellent. So we will go ahead and we have a couple questions here I would like to get answered. So I'm going to go ahead and put this out to the group, and if you have some additional questions, please go ahead and just send those to us and we'll get to them. So first question, is the protocol DevSec only relevant to the endpoint?
Yeah, that's true actually. So if you look at the, so I did describe a C6 device as being, a set of components on ports, and those ports are essentially on PCI ports, and then when you discover the C6 ports, they would appear as endpoints, which means that they would be discovered through a bus mechanism, and there would be basically there would be physical functions on that bus. Yeah, so they would be endpoints. That's correct.
Just want to be clear. Inside endpoint, it's implement inside endpoint communication between that follow this protocol.
And there is a DVSec for the host as well. So if you're implementing a design, right, there is also a on the host root complex.
Okay, thanks. Next question. Can we connect two C6 hosts with different SAM configurations for extended system processing? Anyone want to take that one?
Can you repeat the question?
Could you repeat that, please?
Yes. Can we connect two C6 hosts with different SAM configurations for extended system processing?
I think the extended system process, I'm not quite grokking what is meant by extended system processing.
Oh, I think, Charles, he's saying, he or she is saying, can you basically do a NUMA type configuration? Can you use C6 as a chip-to-chip interconnect? Is that the question? I assume it is.
Okay.
The answer is you can, but you have to have a common view.
Yeah,
at
exactly.
a global level.
I was going to say there is such a thing as a global SAM, right? To be able to move threads invisibly between the two, and for the processes, and for that to still working, there has to be a global system address view.
Okay. Very good. Let's see here. Does C6 support two host connections? How would global memory what would a global memory map look like in that case?
So can you repeat? So it's the idea of having a C6 system with two, like a multi-root type thing. Maybe this is what this question is getting at.
Yes. Does C6 support two host connections? How would global memory map look in that case?
Yeah, I think this is a standard. Right? Most of the server are 2P servers, right? So
I think the question here is about having effectively multiple routes, which I don't think is. I mean, John, maybe you can comment on this, but I don't think this is something we tackled in the C6.
We discussed it from a multi-segment point of view. So there's two answers depending on.
Yes, that's true. That's true. Depending on what the question was.
If the question was where KangKan was going, which is can you have multiple host interfaces, multiple root complexes? The answer is we would expect in that case that you would have a private proprietary interconnect between a 2P system, and each one would be, each root complex would have a downstream topology that would be, part of the overall, overall it would be one system. But you could also have different PCI segments. So you could have isolated C6 topologies running off each segment.
Yeah.
Correct.
But I think if the question is more about having two distinct hosts running two separate operating systems or two separate computers that happen to magically be able to share C6 devices or memory, that's not something that we've looked at, right? If that's
Yeah, I
what the
think
question is.
because the the addresses would be specific to a given host, right? So then they'll have to straddle both hosts at once, and I don't think we have that comprehended yet.
I think it's important to separate what's possible from what we specified, right? So the guide is covering what is kind of not prescribed, but what we've specifically been involved in defining use cases for. And then there's what could you use C6 for? You could use C6 to solve all of those problems, but in this generation, what Charles and Thanu have discussed in the software guide that they are driving is, basically the use cases that we are specifically covering, if that makes sense.
Yep, that makes sense to me.
Okay, here comes the next question. And I think there's actually a follow-up to it here as well. How many RAs can we have in a single C6 system? Can we have a cascade fabric topology? And the follow-up, which I think I'll go ahead and forward to you as well. Can we have peer-to-peer transfer done as part of the C6 system? For example, the initiator is some accelerator / RA, and the destination is another RA.
Well, RA to RA is definitely not something that is part of the
I think
protocol.
No, I think hang on. It's if you set a C6 device to a C6 device, absolutely. A C6 device might have an RA and it might have an HA, and two C6 devices could be connecting together as a way of and you could definitely arrange them in such a way that if you want to increase your compute, you just plug in yet another C6 device, and have peer-to-peer communications between those C6 devices. That's absolutely possible. Phrasing it as RA to RA is confusing because of the very precise definition of an RA within the C6 specification. I think the question probably meant more, what if I want to have a bank of accelerators that are connected together, and can I get them together?
Downstream of a route, right? So you could do today like a GPU type situation. You could do that with C6 where you don't have to go through the host, if each one was its own HA as well as an RA.
Yeah.
And there's an agent limit of 64 for each type of agent in the system.
Yeah, that's the first question. So you could have and the agent IDs, and we didn't want to get into these details in this presentation. We took a rather conscious decision not to get into those details, but just for the record, right? So we can have up to 64 agents of a given type in a given system. So you could have 64 RAs, 64 HAs, and 64 SAs in a given system.
Okay, and the last question we have here is there a time frame in which the C6 firmware will be released to open source?
Well,
we are. First is that we needed the specification being in public available, right? Or not public, available to the member. And then the reference project, there's a coordination between different companies. So maybe a different company has their private code, and we needed to consolidate in open source GitHub someplace, right? So that's probably gonna take some time. I will say maybe another half a year that you can, as a member, you can access some kind of a source code, right? Not so far. We don't have a common repository for the source code for everybody. Everybody is doing things independent.
Okay. Well, thank you everyone for some great questions and for participating. Charles, Thanu, and KangKan, thank you for taking some time to explain this, and that will conclude our webinar for today. As a reminder, we are going to be posting this in the members area again so that you can review this at your leisure and download the slides at that time. So with that, thank you all very much and have a great day.
Thanks, everyone.
Thank you.